Hi again, everyone. I hope you're doing well. So, in this class, we're going to continue from where we left in the previous class, which uh, was we did a full adder. In this case, it was able to do an addition between 3 bits, and we saw how we can daisy chain these XOR gates and AND gates to even form a bigger AND gate with more bits that it can handle at a go. And we also did odd ticks, whereby we were able to use a delay line to be able to detect just the odd number of ticks. So for today's class, we're going to do bit switch and inverter and see what the class is about. So hope you're excited. So the level says if components output different values on the same wire, you get an error, which is essentially what we did in the previous one, which was like a circular dependency. And unless we added the OR gate on the odd number of ticks level on that circuit, we wouldn't really, we always get an error, since the input is something else and the output of the delay line to the input also was something different, and we can't have that. That will cause an error. We're told, however, so there is an exception. However, some components have gray output pins. Gray, which is like this. These are not outputting at all when the component is not enabled. This is the case for bit switch components. When the top pin is false, we have a top pin which is called an enable pin. If it's false, that means that this does not output. It's gray. It's different from the other one, which was red, which was an off signal, which means that it's part of the circuit but it's off. But this one is gray, which means it's like it's not there. And I was told when the top pin, enable pin, is false, the output is disabled. This means that more than one of the gray output pins can connect to the same wire and not cause an error, as long as only one of them is enabled at a time. So you can just have outputs coming in to a wire, just a single wire, but the control pin will be this enable pin. So you'll enable this. It's a switch. So let's see. And I think we are supposed to, okay, let's see. Using 2 NOT gates and 2 switches, build an XOR gate. And using 2 NOT gates and 2 switches, build an XOR gate. An XOR gate, again I have to confirm from the definition. An XOR gate checks if the inputs are different. If the inputs are different and fires are 1. So if we have this and this, and they are, let's just imagine they are connected together, and we don't have any other gates, so they are restricting us to just this. If we have this, we should get an off. But if we have one of them as on, we should get an on. But since we don't have like a get here, which means that this is outputting an on, this is outputting an off, the signals on this wire are not the same but linked to the same line, and that's a short circuit. Or yeah, it's a short circuit. I don't know if there's a difference between a short circuit and a circular dependency, but if you know the difference, let me know down in the comments. But it causes an issue, as we can see, since the signals are kind of different. The only hint we get is that we have two pads, and we have a NOT gate and something that's not a NOT gate. So we can just have one line, but then both of these outputting to one line, but that will be determined by which pin is enabled. Right now it's gray. As you can see, this is enable pin. We have input, which is this, and output. And we have used up this. So to detect if the inputs are different, we kind of need to check this and the inverse as well. And also another, maybe this, and the inverse as well. So okay, this is what we would do if we had an AND gate to check, but we don't. So this is okay. So if we have both inputs as off, we want us to get an off, and it's what we do get. If we have our first input as on, that means we want to get an on, right? And we can get an on, but then it's only allowed when the input here is enabled, so on. And if we have both of them as on, this turns it off, so we get an off, which is okay. And then if we have this as on, that means that we can use this other path that we're given, whereby we just enable this switch that way, and use this to enable, since we have to make sure that this is only on when the other one is opposite of what we want. So in that case, it's gonna be, can do this, we extend a bit, then, and I can be sure that that works. This is an XOR gate, but using just the switches and the NOTs, and we can test first input, second, third, and final one. Yeah, and yeah, we're able to utilize this bit switch, whereby the main agenda was that we have just one line, but we can decide which line to use based on what we activate. As long as we don't activate the same line at the same time, and the lines are not different, or rather are the same, we are okay. But if they are different, that's that's an issue. So we always want to make sure that at least just one, at most one, is enabled at a time. And yeah. The next level is a bit inverter. Okay. We're experimenting with how backgrounds influence cognitive functions in Earthlings. Okay, so I guess we do have a new nice background. So let's see if we're able to solve this level a bit faster. I don't know. When the invert is on, output the opposite value. Okay, this seems easy. Otherwise, just output the value as is. As you can see, we have a value invert. Oh, okay. Value as is. Okay, so this is the value. We're told this is a value, and this is invert. Oh, this is like an instruction. So this is introduction to how computer do, or just do instructions. This bit represents a value, and this one represents invert. So if we have this, we have this value, and I'm sure we'll need to use an inverter somewhere, but we can't really. I expected to see the switch that we had before, but I don't see it. The instruction says that when invert is true, output the opposite of the value. So this is false, so the value should just be, let me just use an OR gate for a start. The value should be, if the invert is no, the value is off. That means it's okay. But if the invert is on, the value is off. That means I should invert it, and the output here should be on. Off, inverters, yes, the output is on. But when I have this as on, so maybe an exclusive OR, I'm not sure, but let's see. So if we have our value, everything is off. Invert as yes, that's true. So, and our input is off, so we get an on, which is okay. And if invert is on, and then our output, our input is off. Is it that simple? But if we have our invert as, okay, let me turn everything off. Our invert is off, and the value as on, as off, we should get an off, and if on, should get an on. Really, it's that easy. It's just an XOR. Let me see. That was easy. This level is exactly the same as XOR. One XOR one you solved before. Remember, no matter what we tell you the goal of the level is, the real truth is in the truth table. Yeah, so I didn't even realize that was an XOR. So let's just get rid of this and run again. And yeah, I think the background helped us to solve this, so yeah. And believe we can do the final one, which is a byte, or a byte is essentially 8 bits of data or input signals. You may think it is unethical to eat all the Earthlings that don't win the competition. Of course it is unethical. But actually it's okay because you lived good lives in the wild and you don't let the meat go to waste. Okay, fair. Or we're told or each bit of the input byte and output the results. That should be simple. Supposed to or. We have 2 inputs. We can just type in any number. The binary for, let's say, 40, 46, maybe and maybe 8. And you're supposed to OR it. As far as we know, we can just OR bits. So because we have a byte, remember byte is 8 bits, we need to split it into bits. So let's do a split on this. You can just move it a bit. And another bit. And we need to OR all of this. Like I think I should have like 8 of this OR for each of these bit pair. 4, 5, 6, 7, and 8. And some other to join to get the output. No, we don't need that. We can just use another bit maker at the end to pick the bits that were got from here. And that should be the output. So we're going to match to pair this together. So we can just do the first one and okay, not the first one and the first one. Let's just do this. First one and the first one, the second one, and the second one. This is going to be hectic. Yeah, the lines are going to be just a lot. So maybe let's create a bit of space and maybe Okay, so fast and fast. It's hard to do these lines. Fast and fast. Second and second. Let's just move it a bit. Second and second. Third. Third and third. Fourth. And fourth. Fifth. Oh no. Don't have space. Fifth. And fifth. Sixth. Let's do a sixth. Sixth. And sixth. It's not clean, but 6th and 6th. 7th. 7th, we can just extrude from here. 7 and 7, then 8, which is the final one. You can just pick it from here. 8, and 8, and yeah. And that's it. That's how we byte OR. We take a byte, split it into bits, take the other byte, split it into bits, then pair the bytes, add in each byte the first, second, third, and so on to the 8th, and OR them, which is the operation we are told to do on the bytes, and then finally the OR result we get, we make it again into a byte, and that essentially gives us our final desired out byte. So that's byte OR, and yeah, I believe that's the end of our class, and catch you in the next class. Bye.